Chapter 9, Introduction to Statics and Torque. So, and shows a big rock structure from Australia's Kalbarri National Park, in which all the forces acting on it are keeping it static. And I think I can see a blonde ponytail up there. But statics is the study of forces in equilibrium, which is a special case of Newton's second law in which the acceleration is zero. Here's your standard overproduced American sports-based video. We're talking about net force is zero and the net torque is zero if something's not accelerating.
And the net torque must be zero. Once the squad members achieve both of these conditions, any member can remain in their stance without falling until they are interrupted by an unbalanced external force or change to another position.
Okay, so section 9.1 is called the first condition for equilibrium, which is simply that the net force is zero, meaning that the acceleration is zero. And we've definitely talked about that quite a lot. But the idea here is that just because the net force is zero doesn't necessarily mean that the object doesn't move at all. So they give an example of an ice hockey stick lying flat on the ice with two equal and opposite horizontal forces. So when you draw a free body diagram and you add these two forces, you get zero net force. And that makes sense. This won't move. However, you could do the exact same situation, but apply these forces in different locations. What if I apply this force to the left on the bottom part of the stick and the force to the right on the top part of the stick? Well, the whole stick is going to turn clockwise in this case, right? So the free body diagram looks the same. The net force is zero, but your object now is going to rotate, and that's, I guess, rotation's a form of acceleration, so it's not static equilibrium. Section 9.2 is called the second condition for equilibrium, which is that the torque must be zero. So torque is the rotational equivalent of force, and it involves force. This is an equation for torque, or for the magnitude of torque, which is that you have a Greek letter tau is torque. R is the distance from a pivot point to the place where a force is exerted. F is that force, and theta is the angle between the force vector and the vector that goes from the pivot to where you're applying the force. I think it's easiest if we look at these different diagrams here. These are all showing a door which is being opened, and you're looking a bird's eye view down on the door. So there's the doorknob, there's the hinge, this is a wall or something like that, and you're looking down towards the floor. So in the first diagram, there's a force F being applied up and to the left, and R is that vector which goes from the pivot point, which is the hinge, to where the force is being applied. And this is going to produce what is called a counterclockwise torque. So torque has a direction, which is either counterclockwise or clockwise around the pivot. So you can kind of imagine that if you were to push this door, it would swing up a little, and that is a counterclockwise rotation around this pivot. So the hinge stays fixed and the door would rotate up and to the left like that. And what's interesting is that the force here is perpendicular to the radius r. So theta is 90 degrees and sine theta is 1. So you just get r times f. In part B of this figure, it's the same situation, but now the force is a little less. So you get a little smaller counterclockwise torque. When you compare A to C, now you have the same force, but it's applied at a different distance from the hinge. So R here is less, and so the torque is less. You get less torque when you apply that same force closer to the pivot point. Here in D, you've got a force applied the opposite direction, and what this does is it produces a clockwise torque. So if you can imagine, you're sort of closing the door here, it's going down, well, it's going to rotate in a clockwise direction. So this produces a clockwise torque. Here in E, you have the same force, it's applied at the same distance r, but the angle between the force and the vector r is now less than 90 degrees. And so you'll get a smaller torque in this case. And lastly, in F, you've got the same force applied to the same part of the door, but now theta is 0 degrees. You have a force that's parallel to the vector from the hinge out to where the force is applied, and this produces 0 torque because sine of 0 is 0. So we don't really have a very good word for the symbol r. We just say it is the distance from the pivot point to the point where the force is applied. But what you can do is rearrange this equation a little bit. So you've got F times r sine theta. And you say r sine theta is this r with a little perpendicular sign. And that's called the perpendicular lever arm. So when you arrange it like that, tau is the perpendicular lever arm times F. And that can be a really good way of solving problems. If you have this force applied here and the hinge is at a different distance, then what you can do is find the distance between that hinge and the force line, where there's a line that goes through where the force is applied. You find that the shortest perpendicular distance between the hinge and that force line, that gives you r perpendicular. So it's that perpendicular lever arm times the force gives you the torque. And here's a situation where just different hinges actually give you completely different signs of torque. Here's the, in situation A, the hinge down on the left, you get a clockwise or counterclockwise torque, but if you were to put the hinge above, you would get a clockwise torque from the exact same force. The SI unit of torque is newtons times meters. And the second condition necessary to achieve equilibrium is that the net torque is 0. So, for example, we can analyze this situation with two children on a seesaw. You might say that, for example, the torques have to equal 0. You can find the torques from each of them and work out the distances. But you can also make the net force 0. And in this case, we're looking at the vertical components of the forces and find the force on the pivot point as well. The point is that both things have to be true. The net force in the x and y direction have to be 0. That's two equations. And now a third equation is that the net torque has to be 0. Okay, so section 9.3 is called stability. And it says it's one thing to have a system in equilibrium. It's quite another for it to be stable. The toy doll perched in the man's hand in this figure, this is not a real child, as they say, is not in stable equilibrium. There are three types of equilibrium: stable, unstable, and neutral. If you're balanced in such a way that when you experience a little displacement from equilibrium, such as a little bump, if it experiences a net force or torque opposite to the direction that it was bumped, that's called stable equilibrium. For example, a marble at the bottom of a bowl. If you disturb the marble in the bottom of the bowl, it rolls back towards its equilibrium situation. A system is in unstable equilibrium if, when it's displaced or bumped, it experiences a net force or torque in the same direction as the displacement from an equilibrium. For example, that same marble on the inverted bowl, so it's sitting on the top of a hill. You give it a little bump, well, it's going to accelerate away from its equilibrium situation. If you don't bump it, it can stay there, but as soon as you give it a bump, it just accelerates away. And the system is in neutral equilibrium if you give it a little bump and it doesn't have a force that brings it back to equilibrium or accelerates it away from equilibrium. So then they talk about something called base of support. So what they're saying here is that for any object that is sitting on a horizontal floor, then there's a normal force from the floor on the person, but that normal force can be spread out over a base. And they are saying that if you take the center of gravity of the object and draw a line straight down from that center of gravity, if it falls between the outer edges of the base of support, that means that the object is in stable equilibrium. If you give it a little bump, for example, to the left, then gravity will bring it back down. That'll be the torque, which will bring it back down to the right again. And section 9.4 gives you a problem-solving strategy for static equilibrium problems. So the steps here are: first, determine whether or not the system is in static equilibrium. It's important to draw a free body diagram for the system of interest. Label all the forces, note their relative magnitudes, directions, and points of application. So this is a different kind of free body diagram because you have to kind of draw the object with its size, because you're going to be figuring out torques as well. So I call this an extended free body diagram. And then solve the problem by applying either or both of the conditions of equilibrium. Net force equals 0, and that's really two conditions. This is the net force in the x direction is 0, and net force in the y direction is 0. And the third one is that the net torque is equal to 0. And you choose the pivot point to simplify the solution. Any pivot point can be chosen, but the most useful ones causes torques by unknown forces to be 0. And of course you do your sanity check to see if the solution is reasonable. So they talk about this guy supporting a barbell from different places. If everything's symmetric here, it's pretty simple that Fr equals Fl, and they're both half the weight. But what if he's holding it at two different positions here? So you now want the net torque to be 0. So the way you solve this problem from figure 19.9, here it is, example 9.2. Calculate Fr, the force exerted by the right hand, and Fl, the force exerted by the left hand. The hands are 0.9 meters apart, and the center of gravity of the pole is 0.6 meters from the left hand. So you set the net torque, the torques to be 0. Torque of the right hand equals negative the torque of the weight. That is if you locate the pivot on the left hand. So remember, torques are only measured relative to some pivot point, and you can choose where that pivot point is. If you locate the pivot point at the left hand, then the force of the left hand doesn't exert any torque because it's right on the pivot point, and the lever, the perpendicular lever arm there is 0. So this gives you one equation, and you can solve it out for Fr, and you can also solve out for Fl by, now that you know Fr, you can just use the equilibrium in the y direction. Net force in the y direction equals 0, and that gives you a solution for Fl. And here you find that Fl is half of Fr, as we might have guessed, since Fl is applied twice as far from the center of gravity as Fr. So they sort of have the same torque around that center of gravity. Section 9.5 is about simple machines, and it starts off by defining mechanical advantage. So this is, the idea is a simple machine is just like a lever, gear, pulley, wedge, in which you put some force in and you get some force out. So that's called FO and FI. And the mechanical advantage is what the ratio is of the output force to the input force. And a good example of that is this crowbar. So what happens with the crowbar is that essentially this is a static equilibrium problem a bit in disguise. So at this moment, you're trying to pull the nail up, and everything is, all the forces and all the torques balance. So there is a pivot point, which is right about there where the crowbar kind of touches the ground, and they've tried to put a little line there. And then there's the downward force of your hand applied over here, the pivot, and then an upward force on the nail here. And so the idea is that this upward force on the nail is FO, I guess, and the downward force that you push on the crowbar is Fi, the input force. And so the free body diagram just shows the forces actually acting on the crowbar, so it's just Fi, and this reaction force from the nail, so, and then the normal force from the floor. So I think the nail pushes down on the crowbar, and the crowbar pushes up on the nail. So Fo and Fn are the two forces in an interaction pair, so they're equal and opposite. But what's not fully explained here is that the torques balance on the crowbar. So this downward force Fn of the nail on the crowbar creates a clockwise torque around the pivot. The downward force of the hand on the crowbar, which is to the left of the pivot, produces a counterclockwise torque. And these two torques are equal when it's in static equilibrium. And the torque is computed by multiplying the force times the perpendicular lever arm, which is this R perp. And that is different. There's a long R perp here for the input force and a very short R perp for the output force from the nail on the crowbar, or which is equal and opposite to the crowbar on the nail. So you're balancing torques, and that is what creates this equation, which is the input force times the input lever arm is equal to the output force times the output lever arm. So when you compute mechanical advantage, you get the ratio of these lever arms just upside down. So for the nail puller, the farther you are away here, the greater the mechanical advantage. You can apply a small force with your hand and get a large force on the nail. That's how you can pry out a nail. They also analyze a wheelbarrow, in which the input force, where you're holding the wheelbarrow, and the output force, where you're supporting a load in this center of gravity, they're both on the same side of the pivot point in this case. But now when you draw the free body diagram of this whole wheelbarrow, where this is the center of gravity, there's a downward force of the weight of that center of gravity down, and then your input force is this Fi. And I guess the output force is just saying that you're supporting this against the weight. So there's an equal and opposite force of the weight here. This, I guess the force on the center of gravity is what they're calling Fo here. But really what's happening is that there's two torques. The input torque, which you're rotating the whole thing clockwise around the pivot point, and the weight torque, which is rotating it counterclockwise. And those torques balance, and you can compute the mechanical advantage of the wheelbarrow as being the ratio of these lengths, which is 13.6. And mechanical advantage is not always greater than 1. This is a situation where you've reversed the forces here. Here's your input force on a shovel, and you're supporting this weight. Now the weight is at a greater distance from this pivot, which is over here on the left, than the input force, and so this has a mechanical advantage which is less than 1. So sometimes what you're trying to do is you're not trying to reduce the force that your input, you're actually trying to increase the distance. So if you want to throw a bunch of dirt or something, you want to move your hand a small amount and have the dirt go a little farther to dig a hole, for example. So mechanical advantage can be, you may want it to be greater than 1, or you might want it to be less than 1. Another good example of a mechanical advantage which is purposefully less than 1 is a bicycle. When you press the pedals on your bicycle, the force that you're inputting on the pedals is much greater than the force that ends up pushing on the bike, but your feet move a small distance and the bike travels a larger distance, so you can increase your speed there. A crank is another simple machine, even just a wheel. So they talk about the force on the axle of a wheel compared to the radius of the wheel. And then there's a lot of stuff here about pulleys. And the idea of these pulleys is that you are looking at a free body diagram of one of the pulleys. And so here we see two tensions pulling upwards and the weight here pulling downwards. So when you pull down here, you're actually increasing the output force. So the output force is 2T, so you get a mechanical advantage of this pulley situation of 2. If you wrap it all around here and use 3 pulleys, then again, looking at the free body diagram for this bottom pulley, you see 3 upward tensions, so you get a mechanical advantage. The output force is 3 times greater than the input force, and you can play around with the strings, use this same pulley situation so that when you're pulling upwards, the total force can actually be 4 times the tension. You can get a mechanical advantage of 4. So what will also happen, the sort of downside of this, is that when you get a mechanical advantage of, say, 2, for example, it means that you have to pull the string twice as far to get the mass to raise up that same distance. So if you pull 1 meter in this direction, then the mass will only raise half a meter, which sort of makes sense in terms of conservation of energy, because the work done to raise this has to be some amount of joules, and work is the force times the distance. So you get a greater force applied to the mass, but it goes a smaller distance. So the work that you put in by pulling this string has to be at least as much as the work that you end up doing on the load. And the last section of this chapter talks about forces and torques in muscles and joints in the human body. So here's a little sketch of someone holding up a physics book, and then here's an extended free body diagram showing the forearm and the different forces that are acting on it. So here's the force of the bicep, here's the weight of the book, which is going to be balanced by an upward force here on the book. Here's the center of gravity of the forearm, and this force is actually a downward force from the upper arm on the elbow. And all of these forces in the vertical direction have to balance to keep it in static equilibrium, and the torques around some pivot point have to balance as well. So we often will choose the pivot point to be, for example, the joint, like the elbow in this case, and balance all the torques, clockwise and counterclockwise torques. And what you get is a really low mechanical advantage, so that the force of the bicep is quite larger than the force that ends up being applied to the book in this case. And that makes sense because the bicep muscle is applying a force really close to the pivot, whereas what you're doing with holding up the book, that's farther from the pivot. So you need to exert a much greater FB than this WB. And it goes on to actually talk about lifting objects with your back, stability. Again, we're revisiting stability that we talked about last time. And there is a rather complicated little example in which you calculate FB, the force of the muscles here on your lower back, in order to keep your upper body in static equilibrium. And that is it for Chapter 9. My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom, where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.